Hi, everyone. So in this video, we're going to discuss arc length, length of a curve. So suppose you're given a function. Let's say your function y is a function of x. So if that is your function where your y variable is isolated, we can determine the length of the curve given the interval from a to b using this formula. So it's the square root of 1 plus the derivative of the function. So we call it dy dx square integrating respect to x. So that is the formula if your function is given in terms of x. Now, however, sometimes our function might not be given in terms of x, you might be given in terms of y. So you might have x is a function of y, let's say g of y. In that case, you use the similar idea, but you're going to set up the integral. So the length will be integrating from c to d. So those are the bound along the y. And you're integrating 1 square root of 1 plus dx dy. So you'll take the derivative of this respect to y, and you integrate respect to y. So that's how the formula changes. So if your function is given in terms of x, you use the first formula. If you're given in terms of y, you use the second formula for convenience, of course. Let's take a look at two examples, one for each. So for the first problem, we're going to find the length of this curve, which is a function of x. Remember, y is isolated. We're defining y in terms of x over this interval. So those are the bound on integration, our limit of integration. So, and the second one, we're going to be looking at finding the length of this curve, where this function is given in terms of y, and here are the bounds on y. So you see the two problems are very similar, but we solve for different variables, so you can set up the integral in two different ways. Or sometimes it's convenient to just set it up in one particular way, depending on what's given to us. So for number one, our curve y is given as ln of secant of x, and we're going to find the length over the interval from 0 to pi over 4. So we want to know what is the length of the curve on that given interval. So we're going to use the first formula I illustrated earlier. The length of the curve is equal to the integral from some a to b of the square root of 1 plus dy dx. So you find the derivative respect to x, you square that, and then integrate respect to x. So we need to figure out what dy dx is, and then we're going to square that, and then we're going to add 1 to it, take the square root of it, and then set up the integral. So let's do one piece at a time. So first, we're going to compute dy dx. So the derivative of y respect to x. So we're going to go ahead and differentiate this. Derivative of using the chain rule, this is going to be 1 over secant of x times the derivative of the inside derivative of secant is secant x times tangent x. And then further simplification, we see that secant on the numerator and the denominator, they cancel each other. So this will give us simply tangent of x. So that's the derivative. Now we need to square the derivative and add 1 to it. So we're going to take our expression, what we got for dy dx, we square that. So we got tangent, we simply square that. So it's just tangent squared. And then we're going to take that and add 1 to it. So 1 plus dy dx squared, that's just going to be 1 plus tangent square of x. Now we know this is an identity. This is equivalent to secant square of x. So hopefully you know your identities. So the expression we're going to substitute for 1 plus the derivative squared is going to be secant square. So that's where I'm going to sub in right in this under the square root. So our length of this curve from the interval of looking is from 0 to pi over 4. So this is the integral from 0 to pi over 4 of the square root of secant square of x dx. So notice that I computed these pieces separately. First, I found the derivative, then I squared the derivative, and then I add 1 to it. And then I get an expression, put it under the square root. Now I simplify and integrate. So if I simplify this, so we know the square root and the square will cancel. And within the interval from 0 to pi over 4, secant is positive, so no need to throw in the absolute value. So we know this is the integral from 0 to pi over 4 of simply secant of x dx. And I hope you remember this integral. This is simply going to be ln in absolute value of secant of x plus tangent of x, and we're going to evaluate from 0 to pi over 4. So that integral, I would recommend you to strongly memorize, or at least see the derivation once. Okay, now we plug in the upper limit of integration. This is ln of secant of pi over 4 plus tangent of pi over 4 minus the lower limit. That's going to be ln of secant of 0 minus plus, this is plus tangent of 0. And we know tangent of 0 is 0, so this will go away. Secant of 0 is going to be 1. So ln of 1 is 0. So this is also 0. So all of this will evaluate to ln of secant of pi over 4. Now note that cosine of pi over 4 is 1 over square root of 2. That means secant will be the reciprocal of that. So secant of pi over 4 will simply be square root of 2. Plus tangent of pi over 4, we know that's 1, so that will simply be 1. And there you have it. This is our length of the curve. You can leave it right here, or you could put it in a calculator and get an actual numerical value. Here, you don't have to keep the absolute values, but I'm keeping it. I just chose to keep it. But if you want to drop the absolute values here, that's totally fine, because square root of 2 plus 1 is a positive number. Okay, now let's take a look at the next example. So the next example we're going to do is this one right here. We're looking at the length of this curve, which is given in terms of y, and the interval is also given along the y. So let's go ahead and proceed. So for this problem, we are going to use the second formula I illustrated. Our L, or the length of this curve, is going to go from some limit of integration, let's say call it from c to d, of the square root of 1 plus. Now instead of dy dx, this is going to be dx dy. So we're going to differentiate respect to y, then we square that, and we integrate respect to y. So these limit of integration belongs to y. We're integrating respect to y. So your integrand should look everything in terms of y. Okay, so let's go ahead and take the derivative. So we're gonna before I differentiate, I'm gonna go ahead and simplify the function a little. Then so that way differentiating it is easy. So x is a function of y. I'm gonna go ahead and rewrite. So this is 1/3 y to the power of 1/2 times y minus 3, and then I'm going to go ahead and distribute. So this will give us 1/3 y to the 1/2 times y. That's 1/3 y to the power of 3/2. Adding their exponent, minus 1/3 y to the 1/2 times 3, -3. That's just going to give us -1 y to the power of 1/2. All right, so that's a nice simple function to take the derivative of. So we're going to take the derivative with respect to y. Let's just call it dx dy. And this is going to be what? So we use the power rule for each term. Differentiate this because it's easier to look at. So you bring down the power, subtract 1 from the power. So you'll have 1/2 y to the power of 1/2 when you take the derivative of this term. When you take the derivative of the second term, you'll have minus 1/2 y to the -1/2. All right. So that's what it looks like. Now we're going to take our derivative expression, which is dx, the dy, and we're going to square that. So before plugging all of this into the integral, we want to simplify and figure out each pieces. So that means I'm going to expand this term. So rewrite it this way. So we have 1/2 y to the 1/2 minus 1/2 y to the -1/2. Another of the same factor, 1/2 y to the 1/2. Let me just rewrite. Minus 1/2 y to the -1/2. So that's what I mean by take the derivative, you square it. And if you distribute this term by term, so remember, distribute this, this and that, this and that. So it's a little bit of work, but again, be very patient with this problem. So this is going to be equal to 1/4. I have y, and then so the second terms will give me -1/4 minus another 1/4, and the last terms will give me positive 1/4 y to the power of -1. So that's what I get. Now let me simplify this before I continue. So I have 1/4y minus 2/4 plus 1/4y in the denominator because of the negative exponent. Now here I'm going to rewrite this term one more time. So this is really y/4. So let's put them in common denominators. So you want to write all of these terms over same denominator, which will be 4y. That's the common denominator. So this fraction has a 4, so I just need to multiply by y/y. So that'll give me y². Now this fraction has a 4, I just need a y. So I multiply by y/y, so that'll be minus 2y. And the last term, I already have a 4y, so I don't need to multiply by anything. So I put them in this forms because you'll see it'll look nicer when you plug this into the integration. So that is the dx dy squared term. Now we need to add 1 to that term and then take the square root. So let's go ahead and do that. So our expression for 1, now we do 1 plus dx dy squared. So that's going to be 1 plus all of that, y² minus 2y plus 1/4y. And then you can put them in common denominator, multiply this by 4y/4y. So you'll see this will become y² plus 2y plus 1/4y. So remember, I'm writing this as the same denominator as the second fraction. So I multiply with 4y/4y. And then combining like terms, that gives me that. So that's my expression for 1 plus the derivative square. So that's where I'm going to substitute under the square root in the integration. Okay, so our length, it's going to be the integral from, so our bounds on the y is from 1 to 9. So we will set it up from 1 to 9 of the square root of that expression. So we have y² plus 2y plus 1/4y dy. Now again, you want to simplify this further. So I could have continued right here and rewrite the numerator. So the numerator can be factored. So this is really y plus 1 times y plus 1/4y. And the numerator, again, you can rewrite it as y plus 1 squared over 4y. So I think I want to substitute that up here instead of what I had before. So that is a better way to actually write this. Because of the square root, we want to simplify the interior as much as we can. So that's where I'm going to put right here. Okay, hopefully you see that. All right, now this is a good problem to work on. It's not so difficult to integrate. The algebra was a bit heavy, but we can now continue. So this is equal to the integral from 1 to 9. I separate the square root. So we get the square root of y plus 1 squared over the square root of 4y dy. Now on the numerator, we can simplify. The square and the square root will cancel. Again, no need to throw in the absolute value because we're in the positive interval. So on the numerator, you'll simply have y plus 1. The denominator, you take the square root of 4, that's 2. And square root of y, we can't really do much. So just write as square root of y dy. And now here, I'm going to go ahead and simplify further. So I will take out the factor of 1/2 because I have a 2 on the denominator times the integral from 1 to 9 of y plus 1 over square root of y dy. Now here, since I have a single term on the denominator, 2 terms on the numerator, I separated them into 2 fractions like this. So you'll have y over square root of y plus 1 over square root of y. And now we integrate each term respect to y. Now before integrating, again, simplify these guys and rewrite. So this is 1 over 2, the integral from 1 to 9. So y over y squared, that's really y to the power of 1/2. So this is just y to the power of 1/2, plus the second one is y to the power of -1/2. And now we integrate using the power rule of integration. So we have 1/2, the first term when you integrate, you'll have y to the 1/2 plus 1. That'll give you a y to the 3/2 over 2 over 3. And then for the second term you integrate, you have y to the power of 1/2 over 1/2, which is same as 2. And now we can evaluate this from 1 to 9. Okay, so let's plug in the upper limit. Now you could also distribute the half out. So I'm thinking I'm going to keep it. Actually, no, I think I'm going to distribute it. It's easier. I just noticed they simplify more. So this is continuing. We have y to the power of 3/2 over 3 plus y to the power of 1/2. And now we can evaluate from 1 to 9. So plug in the upper limit and the lower limit of integration for each y. So we'll have 9 to the power of 3/2 over 3 plus 9 to the power of 1/2 minus 1 to the power of 3/2 over 3 minus 1 plus, this is 1 to the power of 1/2. Okay, now let's simplify. So this will give me, so this number, this is really just taking square root of 9 and then cubing it. So that's really 3 to the power of 3 over 3. So that's 3 squared, which is 9, plus square root of 9, that's 3, minus 1 to the 3 over 2, that's just 1 over 3. And then 1 to the half, that's also 1. And all of these numbers, if you combine, you'll have about 32 over 3. All right, so that is our length of this curve between the given interval 1